Okay, so for this first one, we're going to take iron and react it with hydrobromic acid. So I've got Fe solid over here. And what's the formula for hydrobromic acid?
HBr.
HBr. And what state are we going to put that in?
Aqueous.
Aqueous. What are our options for acids?
Soluble.
State.
Oh.
Aqueous or what? Gas. And so this would be tough to work with if I had iron solid and some hydrobromic acid gas, so aqueous is what we almost always work with. And so what am I going to have on the other side here?
Yeah.
Hydrogen and what?
Iron, bromine,
Oops.
FeB.
So you probably put FeCl2? Or did you put FeCl3? Did you not put any extra CLs? Do you want me to?
CL or DR?
Oh, I'm sorry.
That's why I was like, what did you get that
Just,
one?
just open your mouths. It's really easy. So FeBr3 or 2?
I put 3.
Did everybody put 3? If you look on the table and you find the oxidation states, for iron there's 2. One of them's bold. So that's the one that's going to happen most often. And the one that's bold is 3. So FeBr3. And it's also going to be aqueous, right? What kind of compound is this? Ionic. So it's a salt. So it can be soluble or it can be a solid. And how come this one's soluble?
Bromine.
Bromides are soluble. And where'd the water come from? The hydrochloric acid showed up aqueous, right? So that meant it was dissolved in water, so water was around. The reaction happened in the water. How come it's H2 and not just H?
Something about it can't be H. It has to be 2 H's.
It does have to be 2 H's. Why?
Because you'll never find a single hydrogen atom by itself.
How come? You're correct. Because hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine are the diatomics on the periodic table, and they're never found independent of each other in elemental form. Okay. So I start off with 125 grams and 175 grams. What's going to be left? Oh, we're not finished with the one up top. What do we need to do? Going to need to balance that, right? So what do you want to put?
Two in front of the H, the hydrogen bromide.
The hydrobromic acid. If I put a 2 there, my H's are balanced, but my Br's are not. We see that? So I'm going to get rid of that too. What's the problem with this one? Mathematically, what's the problem? There's an odd number of Br's on the right-hand side and an even number of H's on the right-hand side. And on the left-hand side, there's one of each. So if I make modifications to one, I'm going to change something about the other, which is going to go back and make me change the first thing I changed. So the easiest thing to do is make this thing here even. So how do I make an even number of BRs? Yeah, so if I put a 2 right here, now I've got 6 bromines on my right, and so what do I do on my left? Put a 6 right here, and then I can put what? A 3 in front of my H2s, and then a 2 in front of my iron, and I'm good. Okay. So if I start with this 125 and 175, what will be left in the container when the reaction's over? Okay. So we'll start off with 125 grams of iron. So what am I going to do first?
Convert it to moles.
So count it by converting it into moles. So 1 mole of Fe, 55.847 grams of Fe. So I just counted my iron atoms. But I don't want to know about iron atoms. I want to know about everything that's in the container. So what do you want to try to figure out? Make it easy on yourself.
H2.
Yeah, I'd figure out how much hydrogen is going to be made from this. So for every 2 iron atoms, or 2 moles of iron atoms that go in here, I get 3. I get 3 moles of H2. And then for every 1 mole of H2, I've got 2.0159 grams of H2. Where'd that come from? Just adding up 2 hydrogens, their total mass. And let's see, what does this calculate out to be? So 125 divided by 55.847 times 3 divided by 2 times 2.0159 equals. I got 6.77 grams of iron, or of hydrogen. Okay. So what did this railroad track just tell us?
For every 125 grams of iron, that much hydrogen.
For every 125 grams of iron, I can make 6.77 grams of hydrogen gas if
Have that much other stuff.
I have enough hydrobromic acid to make sure the reaction goes to completion. So we don't actually know that. So now we're going to have to do this calculation for the hydrobromic acid and then ask the same question. So if I've got 275 grams of HBr, for every 1 mole of hydrobromic acid, what is it? 79.904 plus 1.0, 795. It is 80.9835 grams of HBr. And then for every 6 HBRs, I will be making 3 hydrogens. And then for every 1 mole of hydrogen, I'll get 2.0159 grams of hydrogen. Okay, so let's see. 275 divided by my mass of a mole times 2.0159, and I get 3.42 grams of hydrogen. All right. So this second railroad track is telling me what?
The hydrobromic acid is the limiting reagent.
So I know that because the hydrogen is the least produced if I start with that amount. So what we're saying is if I had 275 grams of hydrobromic acid, the instant I've made 3.42 grams of hydrogen gas, what happens?
Then you run out of hydrogen.
I run out of hydrobromic acid. So can I ever make that 6.77 grams? I cannot. I just completely run out of it at exactly 3.42 and the reaction's over. So what do I know is in my container? I know I have 0 grams of HBr, right? That's going to run out. I know I have 3.42 grams of hydrogen gas. Bless you. I need to do another railroad track to either determine how much of the iron was used or how much of my iron 3 bromide was created. So I'll just do the iron one. So if I start off with my 275 grams of HBr, 1 mole HBr, 80.9835 grams HBr, 2 mole iron to 6 mole bromine. And then for every 1 mole of iron, it's 55.847 grams of iron. So what is this railroad track telling us?
Basically what's left.
No, it's not basically what's left. It's not what's left of the iron, it's how much iron was used.
No.
So what this is saying is if I had 275 grams of hydrobromic acid, how much iron would I need to go along with that so the hydrobromic acid and the iron both run out at the same time? And that value is 63.2 grams of iron needed. Okay, so if I started with 125, then that means I'm left with 61.8 grams of iron in the container. So how can I fairly easily figure out how much iron 3 bromide is going to be in the container? Anybody?
So you just subtract that from the combination of grams from the iron and the hydrochloric acid.
The how much stuff went into the container? 400 grams of stuff went into the container, right? So if 400 grams went in, then I gotta have 400 grams when I'm done. None of it is HBr, only 3.42 grams is hydrogen, 61.8 grams is leftover iron, and so all of the rest of the 400 grams has to be the only thing we haven't calculated, which is gonna be our iron bromide, iron 3 bromide. Whatever mass goes in, all that mass has to come out. We could have done a fourth railroad track, just like the second and third railroad track, except we would have gone to the iron 3 bromide, and that would have given us 335 for our answer, but it was easier for us to just do some subtraction. So the same question, right? Do you think there's a chance you might see a question like this on the test? Possibly. Good chance. First, let's go with states. What do you think? That first one, what kind of compound did we call that? Say again? It's definitely a covalent compound. We had a sort of common name for a compound composed of those things that you've heard before used. It's a hydrocarbon. So like methane, ethane, and propane gases were hydrocarbons. Gasoline is a hydrocarbon. So what state do you want to put down for this guy? I would put a liquid down for it because our number was 3 carbons in a hydrocarbon to turn into a liquid. So the first 3 are gases, after that are liquids, and 10 is pretty close to 8, and 8 is gasoline. So it's probably a liquid, and it is. And then the chlorine, because it says on the table, the carbon, solid, and the hydrochloric acid. It's actually a gas. There's no water present, and it was just made. So when we use it, it's aqueous. So 99% of the time, if you have an acid and it's on the reactant side of the equation, the left side, the thing is going to be an aqueous because it's easy to use. And on the right-hand side, if I just actually created the gas, it's going to be, if I just created the acid, then it's going to be in its gaseous form. Balancing it, what do you want to do?
Put the 10 in front of the carbon.
Okay. 10 carbons. What do I put? A 16 here for the hydrogens. And then put an 8 here in front of the chlorines? Okay. So I'm going to start off with 125 and 275 of each of these things, and we'll find out what's left in the container. So we're really just doing exactly the same thing we did last time with different stuff. So 125 grams of decane. Actually, it's not decane. It's close to decane now. So we've got 12.011 times 10 plus 1.075 times 16. So this guy's got a mass of 136.237 grams. And then for every 1 mole, C10H16, what do you want to go to? Yeah, just easier. 10 moles of carbon. And then for every 1 gram of carbon, for every 1 mole of carbon, it's 12.011 grams of carbon. So I've got 125 times 10 times 12.011 divided by 136. And it's 1110.0 grams of carbon's going to be made. Okay, so what does this tell me?
That for every 125 grams of that, you can make 110 grams of carbon.
So if I have 125 grams of C10H16, I can make 110 grams of carbon if
You have
enough chlorine gas to make the reaction run. Okay, so now we're going to do the exact same thing, except this time we're going to say, if I've got 275 grams of chlorine gas and as much C10H16 as I need, how much carbon am I going to make? So we'll go 275 grams of Cl2, 1 mole Cl2, grams Cl2, so it's 35.4, what is it? 53 times 2. And so I've got 70.906. And then for every 8 moles of Cl2, I get 10 moles of carbon. And then for every 1 mole of carbon, I get 12.011 grams of carbon. Okay, so 275 divided by the 70 times 10 divided by 8 times 12.011, and I get 58.2 grams of carbon.
Why did you put 8 moles of carbon?
What did I put?
Isn't it 10 moles of carbon?
It is 10 moles of carbon.
Oh. Never mind.
Does this look like an 8? I know it.
I need glasses.
I know it's bad, but I don't think it looks like an 8.
I didn't see that.
How about that? Okay. So this reaction, these reactants get put into a container and they start reacting, and then what happens?
They separate the carbon. They do a signal replacement.
No.
You burn off the Cl2 first, because it's the limiting reagent.
The chlorine reacts, and the moment the chlorine reacts with the C10H16 to make 58.2 grams of carbon, what happens? I ran out of Cl2. It's gone. So my chlorine gas is my limiting reagent. So right now what I know is inside this container, there's going to be 0 grams of chlorine gas after the reaction's over. There's going to be 58.2 grams of carbon, and I don't know anything else. So I'm gonna have to do another railroad track. So we'll go 275 grams of chlorine to 1 mole of chlorine, and then I'll put 136 grams, 136.237 grams of C10H16 to 1 mole of chlorine, and then I have 1 mole, no, not 1 mole of chlorine, 8 moles of chlorine to 1 mole of C10H16. And then for every 1 mole of C10H16, it's, dang it, why'd you guys let me write that down there?
I was gonna say that.
Just just say it. Like, hey, idiot, go back to where you were a second ago because you screwed that up. Because those things can't cancel each other out. Because my 136 has to go over here. 36.237 grams of C10H16. Does that look better? Okay. And so 275 divided by my 70 number, divided by 8 times my 136 number, and I get 66.0 grams of C10H16. So that's how much I needed to use, but I had 125, so 125 minus 66, and I get 59. So there's going to be 59 leftover grams of C10H16. So how much hydrochloric acid was made? Well, I can take 400 minus 59 minus 58.2, and I get 283 grams of the HCl made. Isn't that working? Okay.